Welcome to another video of Learn with Vishrant Basla. Namaste. Linden cycle, free expansion through a valve. The Linden cycle was the first successful industrial cycle for the liquefaction of air that involved compression, purification, heat exchange, and free expansion through a throttle valve. The air was first compressed at a pressure of 200 bar. In the pre-purification phase, the air was first passed through a solution of 15% lump caustic soda in water for the removal of carbon dioxide, and then passed through a towel filled with dry lump caustic for the removal of entrained water and water vapor. As many be imagined, this method of purification was not very efficient and plant had to be stopped almost every week for the complete dreaming. Strangely enough, this method of purification continued for over 50 years. The purified process air then entered the primary heat exchanger system contained in an insulated cold box. For the pre-cooling of the process, air is countercurrent heat exchanged with the outgoing colder products. Downstream of the heat exchanger, the air passed through a throttle valve, undergoing a Joule-Thomson free expansion with a slight decrease in temperature. The cooled air was then recycled through the primary heat exchanger system, where it cooled down the incoming process's air. Obviously, the cooling effect at the start of the process was minimal. After a long period of time, however, the process air coming out of the primary heat exchanger was sufficiently cool and near its dew point, around 100 K. So it became partially liquid after its expansion through a valve. The liquid portion could then be withdrawn and so look at this again. I think we need this somewhere else. The uncondensed vapor portion could be recycled to maintain a temperature balance throughout the entire system. In the first Linden cycle, figure 2.3, the refrigeration available was very small because it operated at almost constant enthalpy. The small drop in temperature was provided by the kinetic energy of the molecules in the expanding gas and not from any work done by the gas itself. A thermodynamics energy analysis of the original Linden-Hampson cycle indicates the following. So when P is constant, the temperature increases. Now here the temperature is constant, and the entropy is decreasing when temperature is constant, and pressure, well, what is the pressure happening? I don't know. Over here the pressure is increasing, okay. And again, coming here back to this, let's see the refrigeration system. Makeup gas, MF, M, W work done, Q heat, and this is happening and liquid is formed, okay. Gas from that compress is done, where work is done, and heat is removed. It should be removed, because it should be cold. This liquid should be cold. So it goes to heat exchanger. This is the heat exchanger, and let's see how it works. Theoretical analysis of the first Linden high pressure cycle, assuming a steady flow to the combined unit involving the heat exchanger, expansion throttle valve and receiver, and applying the first law which states that 0 equal to m minus mf h1 plus mf hf minus ms2. Liquid yield is given by y equal to mf divided by m equal to h1 minus h2 divided by h1 minus hf. Example: in the application of the simple original and thermodynamically perfect Linden cycle, and assume the following gas property value of nitrogen if the latter is the refrigerant, then H1 equal to 4, this all, okay, so 462, H2 equal to 432 joules per gram. The liquid yield therefore from the equation is, and the work done per unit mass compress is, and work per unit mass liquefaction is like this. So from theoretical analysis of Linden basic cycle with proceeding, let's do another class, okay, because yeah, we'll go more depth into it. Thank you for watching. See you another video. Take care. Bye bye.